Okay, welcome back. Yes, there is less talk. Actually, there's less talk on this workshop. This will be given by Professor Zener from Hong Kong. Yeah, please give me the time.
Thank you very much for inviting me here, and I'm very happy to give the last talk of this program. And sorry, I won't talk about flatbed. Actually, I thought you may get tired after 2 weeks of flatbeds, quantum geometry, but I try to bring you back to some easier problems. And yeah, so this problem is exciton insulator. So I'm going to talk about what's the unique properties of this exciton insulator. I'm going to propose 2 interesting properties. One is the so-called electrical breakdown. The other one is the quantum capacitance. So this work has been collaborating with my student Yuelin Shao from IRP, and I'm Shidai from Hong Kong University of Science and Technology. So first of all, let me explain to you what is exciton and what is exciton insulator and what is exciton fluid or even superfluid. So first, exciton. So excitons are very simple. So suppose we have a semiconductor and we have electrons and we have a hole. Electron and a hole, of course, they live in different bands. But in real space, because they carry opposite charge, there's a foreign attractive interaction between these 2 types of carriers. So one electron can pair with one hole to form a bound state. So this bound state is called exciton. And suppose we have many of electrons and many of holes. So if the number of electrons equals to the number of holes, so there is a possibility that with each electron will finally find its partner to pair, and the system will become exciton, like we'll have many excitons. So then what's the ground state for these many excitons? Because excitons are boson, right? It's formed by 2 fermions. It must be a boson. So the ground state of many bosons, we may immediately jump to the conclusion that it may be a boson-Einstein condensation. So after condensation, it becomes exciton superfluid. But excitons are not that if the excitons are not bound very tightly. So if the inter-electron distance is comparable to the average size of the exciton, so that would be very complicated effective interaction among excitons. So, and also in the system we have impurities, disorders, so which can cancel the exciton superfluid phase. And also if our measuring temperature is not low enough, so excitons and also can be in normal fluid phase. But in some cases there's some pinning potential in the solid, which pins the exciton superfluidity. So then it can be just non-fluid. Excitons can be insulated. So this exciton insulator has been used for, this terminology has been used for many years. And in most of the cases, it's not refers to exciton itself as an insulator. It's not tell us that exciton cannot move. It's just an insulator telling us electron and holes are not moving. So if so in that sense, as long as all electron and all holes they found their partner to pair, single particle cannot move, right? So the only thing can move is one electron paired one hole to form exciton. So in that sense, in most of the literature, we call it exciton insulator only refers to a single particle insulator. It can be like exciton superfluid and exciton normal fluid, but in most of the literature, we call it exciton insulator. So exciton insulator can have different kind of situation. So one situation is we start from a normal semiconductor. The conduction band is always above the valence band, and there is a finite band gap. So in that system, if we pump electrons from valence band to conduction band by shedding light, just like our previous speakers proposed, right? If you shed light on this system, if the photon energy can be larger than the gap, I can pump electrons from valence band to conduction band. So then it takes some time, the combination time for electrons to fall back to the valence band. So within that short period of time, the electrons and holes can be approximately treated as a quasi-equilibrium state, and they can pair and form a transit exciton superfluid. So this is, I call it exciton insulator, but in out of equilibrium or quasi-equilibrium. But if we reduce this the size of the gap to such a number that the gap is actually smaller than the exciton binding energy. That means if I create an exciton, I actually can further reduce the energy, right? So then the energy can be generated automatically in the ground state. So with a infinitely long lifetime. So in this case, we call it's a BEC limit, because at my non-interacting part of the Hamiltonian, I still have the positive gap, but the binding energy of an exciton, of an electron hole, can overcome this gap. So this is a typical BEC limit.
It's a kind of instability, right?
It's an instability, yeah.
So what happens with the real material in that case?
In the real material, we see a very soft gap. So the gap can be changed dramatically by increasing temperature. So you only see some tiny gap in low temperature, but once you heat it up, suddenly the gap becomes larger. It's a very soft gap.
Why should the gap depend on temperature?
Yeah, because in the exciton condensation temperature is very sensitive. If you heat it up, it's cross this exciton condensation temperature. So then the gap will, the single particle gap will increase dramatically. So, and if we further reduce this semiconductor gap, we can finally reach a negative gap situation where part of the valence band can be higher than the conduction band, but only in a very small region of the brain zone. So this we call the negative gap. So in case of the negative gap, if we look at the system can be also viewed as I occupy partially the conduction band and also unoccupy partially of the valence band. And the number of electrons in the conduction band exactly equals the number of the holes in the valence band, right? And in the model Hamiltonian, of course, because the numbers are equal, the densities are equal, the electron Fermi surface matches exactly the hole Fermi surface. So this is exactly the Hamiltonian of BCS. If we treat these electron holes as electrons spin up and down in the BCS Hamiltonian, and the attractive interaction of Coulomb interaction replace the phonon-induced attractive interaction in the BCS problem. So in this problem, in this situation, we have very strong similarity with the BCS problem. So we call it BCS limit. So in the BCS limit, it strongly relies on how good the match of the two Fermi surfaces, electron and hole Fermi surfaces. Yeah, but that's one. Oh, okay. Yeah, so this excitonic insulator or external insulator, as I just mentioned, has been used in the literature for over half century. So there are many different meanings. So I just I asked my student to summarize all possible systems which can be called exciton insulators. So this is the photon pumped system which I mentioned earlier, and I think this is the electron hole, small gap electron and hole in the BC limit, and in this talk I will be particularly focused on this kind of system. It's electron hole bilayer system.
Can I ask a question? So when you talk about the BC limit, the bare band gap should be comparable to the exciton condensation energy.
Extra binding energy. Binding energy is a two-body problem. Condensation energy is a many-body problem. They are actually quite different.
So if you have band structure and you have, like, for example, band gap in a generic system, then if you decrease it, then you normally expect that the gap will close before the bare band gap really closes because of exciton.
So this is the most tricky part of this BEC limit. So sometimes I call it this BEC limit because we started from some H0. H0 usually obtained from some LDA calculation. So LDA calculation is some kind of simple treatment of the many-body Hamiltonian. So then the logic is, in the LDA calculation, we didn't treat the Coulomb interaction very well, and because we made a local density approximation, right? So there's a very strong non-local correlation effect in this material that no way we can capture it by LDA. So in LDA, the result is wrong. So they gave this positive gap band structure to start with, right? So then we need to, on top of that, that wrong starting point, put back the Coulomb interaction and treat it in a more satisfactory way, so that we can include the long-range non-local correlation effect. So in case of that, hopefully we can get the correct ground state. So that's but because LDA can be wrong, but it cannot be too wrong. So that means there is a normal state which is quite close in energy with this exciton condensation ground state. So that's why usually this type of phase is very fragile. If you heat it up, it will become normal. In our language, that means BC has been destroyed by heating, or BC can be destroyed by applying some other fuel. Yeah.
Of the physics to construct type bending model, is that to only consider near maybe two bands near the Fermi level?
Yeah, I think in most of the cases, you just consider two bands near the Fermi level, one for electron, one for hole. So that's the essential physics, right here.
Question.
Yeah.
So I'm confused by this terminology.
Yeah.
Insulator. So two slides ago, you discussed BC and BCH. They're both superconductor. Where is insulator?
Oh, the insulator is So in most of the case, the insulator simply refers to the single particle insulator. most like BEC or BCS, they are still fluid of excitons, but an insulator for electron and holes. So electron holes alone cannot move because they combine, right? The only thing can move in these objects is exciton. So electrons, if they want to move, you have to move with a hole. You cannot move by yourself. So there's no current that can pass through, right?
Okay.
If they move with the opposite charge, that's not called current cancel, right? Right. So that's called the insulator, but refers to single particle meaning. Yeah. So there are many early discussions of excitonic insulators. So this is probably the earliest one in English literature. I'm pretty sure that we have some Russian literature, which is several years before, to propose the possibility of having excitonic insulator. But although the theoretical idea has been proposed more than half century ago, until now, we still have very limited number of real materials which we are quite sure about the excitonic insulator behavior. So this is because of two reasons. So first reason is we lack of perfect material, because in like 2 slides ago, I compared this exciton problem with the BCS problem. Right? But in BCS problem, the exact match of the 2 type of fermions, spin up and spin down fermion, they're in BCS Hamiltonian, they're exactly located at the same position. So this exact match is caused by a symmetry, right? It's a PT symmetry, right? But here we don't have electrons from one band and holes coming from another band. There's no symmetry in condensed matter which can link one band to another, right? So in general, the Fermi surface of an electron and a Fermi surface of a hole, in general, they cannot match exactly. So there's always some crystal field effect which distorted the Fermi surface from being a perfect circle. If it's not a perfect circle, so then the electron and holes, they cannot match exactly.
Sorry, you are assuming that 2 electron and hole with
The
same momenta are going to somehow instability.
Yeah, it can be same momentum, can be different momentum.
So if there is a different momenta, then
Yeah.
density of a state only is matter. I mean,
Yeah, right. If it's not located at the same valley, let's call it valley, the center of the Fermi surface of electron holes. So usually they come up from the same valley, but in some situation they come from different valley. So one electron pocket at one valley pairs with another valley of hole pockets. So in that sense, the order parameter carries finite momentum. So you would expect some small charge density, but charge density is the diagonal element of this matrix element. This order parameter is a matrix, right? The one band. So here is the order parameter is placed in the off diagonal position of two bands. So it's still quite different. It's not a classical CDW, but after reorganizing these bands, of course, that there will be a small CDW generated by such kind of off-diagonal matrix order parameter.
Yeah, but you are assuming that there is some perfect hole Fermi surface,
Yeah.
and there is one perfect electron hole, which
Right.
is related
Related by
something.
a common vector Q.
Yeah.
This Q, in most of the case, this capital Q is 0, but it can be a finite capital Q.
So I'm
Yeah.
assuming that suppose that electron and hole, Fermi surface is also being different.
Yeah.
In such case, it is energetically less favorable to obtain excitonic insulator. Suppose one electron.
Well, of course, yeah. So that's why perfect external insulator is so difficult, because it requires these two Fermi surfaces to be identical.
Okay.
once is identical, then the instability will reach its maximum, right? So the other one is it's a lack of a smoking gun experiment, which is to say that even if we have a perfect exciton insulator phase, it would be very difficult to measure it because it carries no current, right? So the first experimental signal for the possible exciton insulator is coming from double well quantum hole system. It's from Jim Eisenstein's group in 1992. They are studying the quantum hole, but with a double well structure. So the double well is made in a situation that it's a perfect symmetric double well. So once they put electron gas into this double well, because these two wells are completely symmetric, there will be half of the electrons filling the first well and the other half filling the second well. So if in one quantum well, the density of the electron reaches some quantum hole plateau, the other quantum well will do the same. So they will contribute to quantum hole. These two wells will contribute to quantum hole effect equally, right? So then we expect to see only even number of quantum plateau, right? But to their surprise, they see a quite clear odd number, which is mu equals to 1, which in terms of this two quantum well, that each of the quantum well is only half filled for the first Lambda level. So this is a puzzle at that time. And after 12 years, Alan McDonough proposed an explanation for this phenomenon is due to the particle hole like attraction between the two different quantum wells. And if both of the quantum well is half filled for the first Lambda level, so you can think about one like layer is electron, the other one is half filled holes, and the electron and the hole can form exciton pairs for the quantum hole states. So after they form quantum hole pairs, they just did some mean field calculation, and they see that after like boson condensation, there will be a gap opening in the bulk and one chiral edge mode remaining on the edge, which contributes this mu equals to 1 state. But this is for the quantum hole system. And then like 7 years ago, Philip King's group actually repeat this quantum hole effect experiment using the two graphene system. So they replace these two double well quantum wells with two layers of graphene separated by an insulator layer. So they also see a very similar one plateau with the very similar physics in the quantum hole system. And later, King Fan Max group, they realized this double layer structure using the TMD system. So they experimentally put two TMD. It's constant diselenide and monoline diselenide, all just single layer separated by an insulating layer in between. It's HDN layer in between to forbidden the direct single particle hopping from one layer to another, but the Fourier interaction can pass through, but not single particle hopping. So then they made such type of device successfully, and then they measured its capacitance, because this system is nothing but a classical capacitor. But if you calculate its capacitance, capacitance is nothing but you putting charges on both layers, a positive charge on one layer, a negative charge on the other layer, and count its energy increasing, right? So in the classical capacitor, we only count its Coulomb energy, right? So that gives you like constant capacitance, which only relies on the shape of the shape and size of your device, right? But if you include other type of energy in the quantum mechanics, you have to include, for example, kinetic energy of the electron and holes. And the classical Coulomb energy here is just Hartree energy. But the electron and holes are quantum objects. You have to also include its exchange contribution to the total energy and the correlation contribution to the total energy. If you include both, then that gives you the quantum correction to the classical capacitor. So this is the classical the capacitor as a function of basically the carrier density. You can see that once the carrier density getting lower, actually they got more strong and strong quantum corrections. So this is the measured capacitance divided by the classical capacitance. So at very high density of electron and holes, the capacitor will reach slowly approaching the atomic the classical value is 1. But then once the electron and hole density is low, the quantum correction become more and more important. Yeah, so this is the same type of measurement as a function of temperature. You see at the higher temperature, 100 Kelvin, for example, this capacitor is very similar, very close to the classical value. But in low temperature, like 10 Kelvin, it shoots up once the density is low. Yeah, so another very important experiment they found is the current drag experiment. So yeah, let me use this particular plot to explain what is current drag. Current drag is you pass the current in the first layer, because this type of double layer electron hole system has a very unique properties, which is a very important breakthrough in this field, is that they separate electron and holes in the system, and they separate it by inserting a very insulating layer, totally forbidden its direct mixing. So then they can put gates on the top and the bottom to independently control electron and hole, so that they can pass a current in the first layer, in the top layer, and measure the current response on the bottom layer. So this is called the drag measurement. So by measure the ratio of the injecting current and the drag current, you can measure how strongly the electrons in the first layer and the holes on the second layer, they are correlated. So if every electron and holes are formed like excitons, so there will be no net current that can pass through this device, right? So then the electrons, if electrons goes from left to right, holes has to follow. So then, because holes carries the opposite charge, there will be a current towards the opposite direction, but with the same amplitude with the initial current. So the drag efficiency or drag ratio must be 100%, right? So 100% means drag ratio means all the electron and all the holes, they are forming excitons. So nothing can move except the excitons. So Then in last year, Kim Fan Max group from Cornell and Feng Wang's group from Berkeley, they like successfully reached almost 100% ratio of the driving current. So this is a very important experiment. Their experiment actually proves there are excitons and excitons can move, right? But still, they need one additional step to prove that the flow is a soup flow. So now they see a flow, but the flow can be soup flow, but also can be normal flow. In order to prove it's a soup flow, you have to measure the mobility associated with such an exciton flow, which is very different.
I have a stupid question. So this is a 2D system.
Right.
I thought in 2D system at finite temperature you're gonna have BC.
Right.
So
It's a KT transition. If it's a soup flow, so it must be a KT transition.
Okay.
But from their experiment, they only see a flow. So most likely it's not a soup flow. It's still a normal flow. But maybe the mobility is already reached very high. But yeah, we need to wait to see their mobility measurement.
Okay, sorry, another question.
Yeah.
So having exciton BC and excitonic insulator are equivalent or they're different ones?
Like exciton insulator, the concept of exciton insulator is larger than exciton BEC. So once you form exciton insulator, from our definition is single particle insulator, right? So which means we have many excitons in our system. But then let's talk about its fate at 0 temperature. So it can have different fate. Superfluid, like both a metal, a glass, right? And but all those three different phases, it belongs to excitonic insulator.
Okay.
Sorry, I have a question about that. Do exciton has some S-frame? I mean, this guy electron that drag this hole.
Right.
Right. I'm just classically thinking that if the speed is being very large, then maybe sometime it get a problem to take it.
Oh yeah, and you mean the electric field strength, right?
I mean, there's some strength of bonding between.
Right. It's very similar to the superconductor. There's a critical current, of course. If you like exceed the critical current, so then you will break the exciton pairs. Yeah. So I will also talk about this. So this is called electrical breakdown. What you said is maybe the current breakdown, but it's related, I would say. Yeah, so in today's in my work, I focused on like how to break such exciton insulators. So we can consider two kinds of exciton breaking phenomena. One is by adding electric field within the plane. The other one is by adding magnetic field along the z-axis. So let's start with the first one. So this is my Hamiltonian. So it's very much like a BCS Hamiltonian with a pairing interaction between electron and the holes. The pairing interaction here is taken by just Coulomb interaction, screen the Coulomb interaction in this 2D system. And then non-interacting part is just a parabolic band for electrons and for holes. And so the breakdown problem of a single exciton is very similar with the annihilation problem of a single atom. So if you add an electric field to a single atom system, so this is the nuclear, there's electron levels, right? So because the electric field has no, it's provide unbounded potential, right? And if you go to infinity, this potential goes to infinity. If you go to minus infinity, this potential goes to minus infinity, right? So then there will be always a finite, maybe very, very tiny, like tunneling ratio for each of these levels, because this potential will go down, go down, go down, go all the way down to minus infinity. So as long as the E field is not zero, there will be a state outside this atom. But with the state manager, with this bounded state, so there will be some finite ratio. If you just do Fermi-Golden rule, this electron will be tunneled from inside to outside. But it depends on how much distance this electron needs to tunnel. In most of the cases, these possibilities only exist on paper, right? Because the probability will be super, super tiny. But this same like picture can also be found in for a semiconductor. For a semiconductor, we have an electron from a conduction band and a valence band. Once we put an electric field along the inclined direction, this is the conduction band bottom, and this is the valence band top. So then, if we apply a finite electric field, this bottom of the conduction band and top of the valence band become like position dependent, linearly position dependent, right? So that would be like this one point on the valence band equal to the other A point on the conduction band. These two states have the state manager. So they have a finite tunneling ratio for electron tunnel from B to A. It's a cross band tunneling from a valence band to conduction band. So the length or tunneling distance for this event is L equals to delta is the semiconductor gap divided by the field strength. So you see, if my field strength is not big enough, this L, the tunneling distance, is very large. So, and we can use just the WKB method to calculate its tunneling probability. It's proportional to this L divided by C. C is the coherent length of my, the coherent length is just basically the spread of my like linear functions in this A and the B bands. So it's usually just the spread is covers several lattice constant. It's a microscopic length scale, but it depends on L. So this probability is proportional to exponential L divided by C. So that tells us once L is reaches the scale of C, then this is called Zener tunneling. Zener tunneling is a single particle tunneling process. So once this small L is comparable to coherent length C, the Zener tunneling strength is going to shoot up quickly, right? But then this is it's called the Zener breakdown. So once this small L comparable to C. But now let's take a look at our exciton insulator to see, because exciton insulator is also, we can see it's a BCS state. Yeah, we are looking at the exciton insulator phase, but in the BCS limit. So in the BCS limit, it's a pairing state in momentum space. It's a pairing state formed by electrons and holes, which having opposite charge. So once you apply an in-plane electric field, you're going to push electrons along one direction and holes along the opposite direction. So if the electric field is strong enough, you can break the pair, right? But we know the BCS wave function is a many-body wave function. So this pair breaking process should be a many-body process, not just a single particle process. So this is the cartoon of this process. So once we consider exciton condensation, there will be a gap opening between this electron and the whole bands by a BCS pairing order parameter. So then if our electric field, in-plane electric field is strong enough, we can break this order parameter and the system will go back to the semi-metal-like. So the way we do the calculation is that we propose a BCS-type wave function. So this is a standard BCS-type wave function. So here we're just using the electron language. So we treat both electron band and whole band by electron operator. So you can think about this creation operator C dagger as an annihilation operator of a whole. Right? So this is nothing but the available positive particle. So yeah, so the BCS like wave function can be constructed in such a way. And with the BCS order parameter, which is here, this alpha k and beta k are the BCS order parameter. And here we consider generalized order parameter, which we keep the full k dependence of alpha k and beta k, and treat it as a variational parameter. So we try to determine all these alpha k and beta k's at each point of each k points in the brane zone.
So can I say that effectively you want to find some coupling, some correlated coupling or coupling between electron developers and hole in a mean field way?
Yeah, in a mean field way, but in an unrestricted mean field way, because we treat alpha k and beta k at each k point as a free variational parameter, and we include electric field. So this is the most important thing. So once we include the in-plane electric field, we have to calculate the polarization generalized by such a BCS mean field like wave function. So each time we got a BCS mean field wave function, we calculate the polarization just using the Berry phase, using the integration of the Berry phase along the momentum space. So once we get the polarization P, so we add this additional energy like P dot E in our total energy. And then we minimize the total energy with respect to all these alpha K, B Ks, beta Ks. Yeah. So here is our results. So without adding electric field, we got a very trivial like S-wave like BCS order parameter. So this is the gap function in the momentum space. So then if you include the finite electric field, you see the amplitude of the gap function is still like a circle, but if you look at the phase of the wave function, it shows some very strong P wave character. So there's a opposite phase along this direction and this direction. So this direction is the electric field direction. So this is easy to understand because once you apply electric field, the system will try to distort itself to generate a polarization, which is parallel to the electric field to reduce the total energy, right? So the question is, once this polarization is getting bigger and bigger once we increase the electric field, at which point the BCS many-body ground state will lose its stability. So this question can be answered by looking at the so-called Heisen matrix, because the mean field ground state is the saddle point with respect to all these variational parameters, right? So then saddle point means it's a total energy take the first order derivative of these parameters. So it must be zero. That's the definition of saddle point. But then if we ask if this saddle point is stable or not, we need to look at the second order derivative respect to these variational parameters at the saddle point. So this is called Heisen matrix. And we need to do this Heisen matrix respect to all the parameters in the momentum space. So in our calculation in the one brand zone, we usually typically take like 2,000 K points. Then there are like 4,000 different variation parameters because at each point, the parameter, it has a real part and the imaginary part. So we take this 4,000 by 4,000 matrix by taking the second order derivatives as called Heisen matrix. So we diagonalize this matrix. So the eigenvalue of this matrix just tell us the energy of the collective mode, right? So that will be always a zero because we are looking at energy collective excitation at the zero momentum, and we always have a Goldstone mode because we are breaking relative Liouvin symmetry between particle and the whole, right? So there's always a Goldstone mode at zero, but then there's another mode, softer mode I call it, getting weaker and getting softer and softer as a function of electric field. Then until it passes zero. So if an additional mode passes zero, which means the previous saddle point is no longer stable, right? So we can plot the total energy as a function of the eigen vector along that direction. So you will see once the electric field reaches the critical electric field, you'll see along that direction, it's the second order derivative become zero. So if you further increase the electric field, you will see that it will go down, right? So the previous saddle point will lose its stability, but you will see the position of the saddle point almost unchanged. So this is a very typical first order transition induced by the in-plane electric field. So many body states suddenly lose its stability due to a complete softening collective mode. Yeah.
Usually these modes which causes instability, they have some physical meaning.
Right.
Have you considered?
Exactly. This is a very good question. The physical meaning of this mode is called plasma. Because if we consider, yeah, it's a plasma, your favorite, but it's a plasma in an insulator phase. Remember this insulator phase, remember the plasma is a relative motion between positive charge and negative charge, right? So in a jelly model, our negative charge electron gas, positive charge lattice, but lattice we treat it as a mass equals to infinity background. They don't move, right? But here, both positive and negative charge, they can move. They are quantum particles. So the relative motion of electron and holes is this motion.
In white lambda
Yeah.
less than 0.
Oh, this is the eigenstates of the Heisen matrix. So which means if the order parameter move towards that direction, the energy, how energy will change, right? So then if you there's a if this move is positive, which means if you move your order parameter along that direction, the energy will increase, which means the saddle point is stable, right? It's still the lowest energy. But if it's negative, which means if you move along that direction, the energy will reduce without a barrier. So that means this state will lose its stability.
So this is,
Yeah.
I want to say something maybe, excuse me. Is it related to a stiffness of the, I mean, the superfluidity of exciton? And
No,
this,
no.
I mean, this electricity, it seems that it's
It's not stiffness of the superfluid. It's yeah, it's just the frequency of the plasma. Yeah.
Sorry.
Yeah.
Is this calculation for single layer or there is a bit also involved here?
A double layer.
Double layer.
Yeah, you have to include the electron layer and the whole layer, two
Okay,
layers. Yeah.
and if you increase or decrease the layer, can you also comment on this stability of this?
Oh, you mean the
Bit?
layer distance?
Yes,
Yes. If I increase the layer distance, I will actually reduce my effective Coulomb interaction. So you see the interaction, the Coulomb interaction here. Oops. Hold on. I think I have the Coulomb interaction at some. Maybe here. Yeah, it's here. D is the distance. So if you reduce or increase D, the Coulomb interaction will be reduced. So the pair will be weaker and weaker. So it's in the experiment, it's the choosing the correct D is very important because you have to forbidden the single particle tunneling, but at the same time, don't spring the Coulomb interaction too much. Right.
Is there any relationship between the this plasma frequency that you talk about and say the and this arises when you find some electric field in the in logarithmic plane? Is there a relationship with that and the binding energy of the exciton?
This is a good question. Yeah, I will take a look, but yeah, I don't have currently. I don't have like immediate answer to that. Yeah, so then we can calculate the breakdown electric field as a function of system size. You see, if we change system size, the breakdown field, the critical field, almost don't change at all. And I can look at this electric field as a function of density, the carrier density. You see that once we increase the carrier density, the system, the Fermi surface become larger and larger, the pairing gap becomes smaller and smaller, and the critical field getting weaker and weaker. And also we can compare our, so this breakdown due to the softening of collective mode, we call it many-body breakdown. And we can compare to Zener breakdown. So then the length of the many-body breakdown is much 2 orders. Typical length of the many-body breakdown is 2 orders larger than the Zener breakdown, which means if you transform it to electric field will be also 2 orders smaller than the Zener breakdown. So Zener breakdown is a single particle breakdown. Many-body breakdown is a collective breakdown. So it's similar with, so this bonding state is like a prison. So we have many slaves in the prison. They try to break this cell, but the single particle breakdown is they try to do this prison break by himself. But the collective breakdown is that all the prisoners, they are working together. They make up a plan to do this prison break together. So because the prison is actually is due to some self-consistent solution. So the prison is actually generated by other prisoners. So if you work together, it's very easy to break it. That's a very good analog between these two, like electron world and the human world. So then, if you look at the IV curve, you will see that a very a very important signature of the many-body breakdown is if you look at IV curve, is once you apply a voltage drop to the Excitonic insulator phase, at beginning I is 0, so then it suddenly jump to some finite current because this electric field has already passed the breakdown field. So then the current suddenly arises. So this is interesting behavior has already been seen in several similar systems in like 2D material. So this is in a double layer graphene, which can, so this measurement has done by Professor Vittelheim in China. So they saw the very interesting IV curve for a double layer graphene system. So exactly like this. So the current is almost 0 until the field reach the voltage reach some critical value, suddenly jump up. So then these different color are the measurement with different with different distance between leads. So you'll see if you increase the distance, you increase the critical voltage. So all these curves, they actually correspond to the same field stress, but because of distance of the leads are different, they have different critical voltage. So this actually agrees with our theory very well. So so my time is almost up. I will quickly go through this interlayer quantum capacitance. But as I already mentioned before, the capacitance, if you want to calculate the full capacitance, including the quantum correction, you need to calculate the total energy of the system with both kinetic energy and exchange energy from the current interaction. So then we discuss the situation when we applying a field, a magnetic field along the z direction. So then all the electrons. So this is the capacitance without the magnetic field. You will see we can exactly get a very similar curve as a function of density with Kim-Fan Max experiments. So the maximum quantum capacitance they can reach can be almost 2 times of the classical capacitance. So in this calculation, we use the parameters. Exactly, the parameters corresponds to their particular material, 2D material, constant diagonal. So then we change to a problem where we apply a magnetic field on the z-axis. So then the electrons and the holes will form lambda level first, right? So then these lambda level electrons will pair. So once they form lambda levels as a function of field strength, it's periodically that one lambda level and of electron and the one lambda level of holes will appear in the Fermi surface, right? With some certain field strength. But then in the other half of the period, they actually move away from the Fermi surface. So once they bring up to the Fermi surface, the pairing strength will be the maximum. Once they bring far away to the Fermi surface, then the pairing strength will be the minimum. So as a function of field strength, the pairing gap will go up and down as a function of 1 over b actually. Yeah, so by including that, we calculate the quantum capacitance. You can see if you plot the B field in the y-axis and the chemical potential, which is the Carrier density on the horizontal axis, you will see this famous lambda fins, which is exactly very similar with those the Haas, not the Haas, Shubakov the Haas effect once they plot resistance. But here we plot capacitance. but we have very similar level of fat. And this can be also a smoking gun experiment for the existence of EI. Yeah, I think I just put a summary here. Thank you very much for your attention.
Now it's open for the question.
So in the experiment that you showed for the this breakdown, it seemed like for positive electric field and
Yeah.
negative electric field,
It's the same.
it's the same.
It must be the same because the system has invariant symmetry.
But if you go look at the experiment.
Yeah,
it
there's a
looks
slight
looks-
difference, yes.
So is it really the same or?
But
or it's just some-
I would say experimental, if you look at the experimental data, I would say almost the same, yeah. But there's a small deviation.
So you can see there's a larger, yeah, you see the red.
Yeah,
for instance, the red.
because it's it has a hysteresis, right?
Yeah,
The hysteresis is larger on the negative side and smaller on the positive side. So that may be due to some inhomogeneity of the sample. Yeah.
is there broken and inversion symmetry in the system?
No, the system has no inverse, but
It has
but there is some,
inversion.
yeah,
Has inversion or no inversion?
it has an inversion, yeah. It's a bundle stacking bilayer graphene, yeah. No, it's not mine. Oh, this is mine? Okay. Yeah. Please.
Sorry, I think I missed your rest parts that
Yeah,
you said that this Landau Venn diagram is
Yeah.
the smoking gun, it's the exciton insulator.
yeah.
Without this, what do you expect in the view?
Oh, I should say, it's one of the smoking guns because it proves this energy gap is very fragile and it can oscillate with the field strength, Yeah. But of course, it doesn't prove that the silk fluid flow in the system. No, it's not a proof of silk fluid. Yeah. But it proves the gap is very sensitive. So that's one of the important features of the excitonic insulator.
Thank you.
So in the model, see two types of terminal operator, an electron on the first layer and the second layer.
Yeah.
But didn't take into account the speed difference. Yeah, like
Yes, that's a good question. Yeah. So here we only consider the spinless fermion. So which means of course we have two copies of spin. So which means this like pairing process is independent of spin. So there will be spin up pair with spin up with pair with spin down, down up, and down down. All four possible pairings are equal. Yeah, but of course there is a spin-related interaction. We'll split these four possible pairing state and pick one. Usually it's spin signal. Yeah.
so in such a case, if the if the exciton form in such a bilayer system is simpler, then can we expect if you apply, for example, here you introduced like applying the out of plane field.
Right.
But if you apply like in plane magnetic field,
As
as in the superconductor, we expect like Pauli limit.
right.
Being the pair. So can we also expect a similar situation in the situation later too?
Yeah, if it's a singlet, yes. Yeah, in-plane magnetic field can break it. Yeah. You're right. Yeah.
So, yeah, I have a question related to this question about this quantum oscillation.
Yeah.
So in excitonic insulator, you have a single particle gap, right? But
Yes, yes.
Till you see the quantum oscillation.
Yeah, the quantum oscillation is not due to the gap. It's due to the underlying Fermi surface.
Yeah, that's how do you understand it? Basically, the spectrum itself is gap, right? But you
Yeah.
see the oscillate like
The size of the gap oscillates.
size of gap is oscillating.
We didn't plot in this slides, but we have a plot simply in the paper. If you plot the mean field energy gap as a function of 1/b, it just make this quantum oscillation. So this is very easy to understand. So once the because as you tune the B field, you will periodically like occupy the lambda level. If a lambda level is fully occupied, it's pushed away from the chemical potential, right? If it's halfly occupied, it's right at the chemical potential. If the lambda levels are right at the chemical potential, the pairing is the maximum. Because both the electron lambda level and the hole's lambda levels, they both appear at the Fermi level. So there's no energy difference. So if they are both fully occupied, so they move away. So electron move up, the holes move down. So there's a finite energy difference between electron and holes, which reduces the gap. But once they both appear at the Fermi level, the pairing will be greatly enhanced.
It's different from the quantum oscillation in the metallics.
No, that's very different. Yeah, it can have some similar plot, but very different mechanism.
You mentioned
It's also related because you can understand the oscillation of resistance also from the fully occupied lambda level and the partially occupied lambda level. Right.
So what determines this frequency? What determines the frequency?
What will be size of the underlying Fermi surface? So what is underlying Fermi surface is the Fermi surface before the pairing.
Before the pairing.
Yeah, if you can see this plot, so that is a Fermi surface before pairing, right? Because we have an equal number of electron holes, the area of the electron Fermi surface equals the area of the hole Fermi surface. So that's the period of the 1/b oscillation.
I can see.
Yeah.
You see that this oscillation, the BCS limit of the X, but not in the BC limit.
In BC limit, we don't have that Fermi surface.
Yeah.
Of course, we don't see. Yeah.
So to be clear, when you condense already, you no longer have the Fermi surface. There is an underlying.
Right.
So
That's why it's called underlying.
Are you saying that the quantum oscillation without a Fermi surface?
Yeah, without that Fermi surface.
So you have quantum oscillation without Fermi surface.
Yeah.
So can I be provocative and ask you a question?
Yeah.
So a couple of years ago, Zener in Princeton had this quantum oscillations without Fermi surface.
Right.
So all sorts of weird things that.
There's a big debate about that.
Yeah. So.
And I think our theory can support his explanation.
So you can get quantum oscillations without a Fermi surface.
Yeah.
If you're an excitonic insulator.
Yeah, if it's excitonic insulator. But unfortunately, Sanfeng Wu from Princeton, they only measure the resistance.
Yes.
I strongly suggest they measure capacitance. But they do AC measurement. So I think it's even from their AC measurement, they measure the resistance within the plane. If they do resistance measurement along the z-axis, so there will be no difference with the capacitance.
Yes, but I guess Patrick Lee was saying that the gap could also oscillate as a function.
Right.
And so then
we have the same idea. This idea is not new. It's because 10 years ago, when people are studying samarium hexaboride, so there's also a big debate of quantum oscillation without the Fermi surface. Yeah, so this idea is proposed by me, I think, 10 years ago to explain samarium hexaboride. And from my point of view, the quantum insulator is a strong coupling limit of the exciton insulator. But qualitatively, there are no difference between quantum insulator and this exciton insulator. They are smoothly connected.
And this would also be one way of differentiating between the various types of excitonic insulators, right? So this is a specific type of.
Right. It's only work for BCS limit.
Yes.
For BC limit, no. Yeah, thank you. Yes.
Can you define topological excitonic insulator?
Oh, yeah. Topological excitonic insulator is very simple. If the system has inverting symmetry and this yellow and blue has opposite the parity, and the pairing is P wave. But it's very difficult to realize P wave pairing.
You need a P wave.
Yeah, we need a P wave pairing. Otherwise, that's not topological. Yeah.
What question is it? This is a dipole shape, is a interlayer dipole, right?
Yeah.
If you give the Boltzmann boson right, excitation is possible?
Yeah, so this dipole along the z-axis, in principle, can have some consequence. But we need to, so the important point is to measure the transport of this z-axis dipole along within the plane. That is not so easy to measure. Yeah, right. So the how these dipoles are move around in the plane.
Summarily.
Yeah, so we're working on some electric effect. Yeah.
Any other questions?
I have one regarding that you told us without electric field,
Yeah.
the excitonic is looks like S wave.
Right.
But when you turn on electric field, then it become more like P wave.
will have a P wave component as well.
So do P wave have a nodes or not?
Yeah, but if it's a pure P wave,
Oh,
of course
P plus S.
Yeah, it's a P plus S.
So in a breakdown limit, can we
that's a
say
good
that
question.
it's just P wave?
Yeah, it depends on the current density. So I think that would be a case that if the current density is not high enough, it's close to the crossover regime between BC and BCS. So then we have quite a strong bonding of electron and holes. And maybe this electron breakdown actually happens at quite large electric field. So at that point, maybe we can see some nodal behavior. Yeah, if the P wave components is larger than S wave components, so that's the condition for the appearance of node. Yeah.
Question? And the second.